So I'm now going to give you the solution for the phase space. So you don't have this term, you don't have that one. And so you're looking at the bifurcation diagram when omega t is changing. You look really at the solution. You'll have three points where this line is crossing the, so this is for example mu as a function of omega t. And so basically you will find that there are two attractors, depending of course if you have such a pictures, and one saddle point. And of course if this does not happen, the situation is going to be different. So I'm going to describe here what happened in that case, and I'll give you to do what happened when, for example, you have you can have a situation like this when no crossing. You can have a situation where you get one tangent, which is here. This is you have a double a critical situation. So how do you do the phase space? The phase space is actually in the variable mu and v. You have to place, so the attractor, this attractor here is going to be located at that point. This is for mu equals 1, this is 0 and 1. And so you have here an attractor. You have somewhere here a saddle point, so this is called the saddle. And you have here somewhere another attractor. So the saddle point goes like this. You have to put here the trajectory that goes. And so this is the unstable manifold. So you can draw locally the picture where everything goes here to the attractor. And then what happened is that, and so I invite you to start thinking about this. You have here exactly a Hopf bifurcation. So you have here actually a limit cycle. And what happened around is that a trajectory can come, make a loop, and generically it converges here and go back to 0, right? And so in here you have these unstable limit cycles where all trajectories here, exactly starting from here, goes here and then can continue going back to 0. While here you have this point is an attractor, so everything is attracted. So this is very important to be able to analyze such kind of equation and to draw really the phase space. And this is going to be very important for the study of when we do a perturbation with noise. This is a noise perturbation. And to finish, I would like to discuss an application and an exercise, which is the following. Suppose you're interested in the following question. You have here a linear or a dynamical system, which can be homogeneous of parameter beta, you know, such that x, a of x multiplied by a constant a is a to the power beta a of x, or it can just be a linear system. So suppose you have one, and then you have a second one, and let's assume that 0 is a critical point. 0 is a critical point for them, for both of them. So now, and 0 is asymptotically stable, and so which means that if you start with dynamical system A and any trajectories, let's say rotate to 0, this is for A, and this is the same for B. All trajectories here of B goes to 0. So I would like to give you as the following exercise. Can you construct a dynamical system Z such that Z of t can be obtained either by choosing A or choosing B? So U of t u of t equals 0 or 1, but let's say not any intermediate value. So you select A or you select B. And the question is, if for both cases, if you stay on A, the trajectory, all trajectory goes to 0. And the same for B. So, however, the question is the following. Can you choose u of t such that z has a limit cycle? That is, by doing a clever choice of u of t, you can switch between trajectories of A, the trajectory of A or B, such that you do not converge anymore to 0, but you stay such that the trajectories do not converge to 0 and they do converge to a limit cycle. All right, so of course, if A equals B, this is not possible. So in some sense, you need A and B to be sufficiently different for this. And once you have such this condition, which is A, that has to be quite different from B, the question you would like to see is how do you find u of t? All right, so for this switching x dot equals a or b x, this is called this is a classical problem of switch systems, which has been addressed by Filipov, by many authors. Filipov, Popov, Russian school, and I invite you to look at the following publication for some method that we developed a couple of years ago on this question, and how to find u of t, what is called the controller that allows you really to use trajectories of A, then you glue to trajectories of B, again you glue to trajectories of A and B and so on, so that you can create a limit cycle and not to fall into the spiral. All right, so this is an exercise that will end this introduction on dynamical system. The next classes will be about the introduction of stochastic processes. So I will stop here, and the next classes will post later on the web. So thank you.